We're going to start this unit by talking about radian measurement and its application. This will be the second page in the packet that I gave you. If you'll open it up and turn it to that page, you'll notice that the notes are actually filled in for you already. So what I'm asking you to do is just make sure you're listening along and following along as I go through this. Make sure you note any questions that you have on the paper, highlight it, so that when we meet in a couple days, you'll have the questions to ask. So talking about radian measure, in class, what I mentioned a few times is that it's really important that you write your degree symbol because there are actually two types of measurements for an angle. So degree is one measurement, but radian is actually the other measurement. And the way that radian actually, or why it's kind of used, has to do with the circumference of a circle. So if you recall how you come up with the circumference of a circle equals 2 pi r. And if you think about what that is, or so the radius is from here to here, and if we establish the radius just to be 1, then the circumference of a circle at 1 unit would be 2 pi. But if we also think about the circumference of a circle and how you go all the way around, it is also 360 degrees. So the 2 pi measurement comes from the radian measurement. So 2 pi is the unit to go all the way around. So 360 degrees is equivalent to 2 pi. So if you think about what that conversion is, if we divide by both sides by 2 pi and reduce it, you get 180 over pi equals 1 radian. So this is one conversion that you'll need to make sure you have written down and you know. And then going the other way, if I have 2 pi equals 360 degrees, and I divide both sides by 360, then 1 degree equals pi over 180. And we're going to use these conversions to kind of go back and forth when we need to at appropriate times. So I just did a couple of practice problems in your notes. And the first one is change 30 degrees to radians. So how do I know which one to use? Well, kind of go back to, when you're doing conversions and science before. What we're going to do for 30 degrees to change to um, radians is we will use this one over here. And so it's times pi over 180. And if you think about why we use that, it's because we know that the units of measurements will cancel out, one being in the numerator, one being the denominator, and radians will be left over. So if we go and we multiply across, we get 30 pi over 180, and that's going to reduce to pi over 6. So 30 degrees is equivalent to pi over 6 radians. Now, if I want to change 4 pi over 3 to degrees, I'll use the other conversion. 4 pi over 3 times 180 over pi. And again, this is because this is degrees. This is starting in radians. And so you can see, hopefully, how those measurements cancel out and we'll be left with degrees. So I can simplify this and this right here. So 180 over 3, that's going to be 60. So, and the pi's will cancel out as well. So 4 times 60 will give you 240 degrees. So again, what this is saying is that 4 pi over 3 is equivalent to 240. So how will you use this? Well, you'll use this when you're evaluating some trig functions. So if I have sine of pi over 6, what we really want to understand is that over 6 is really the same as 30 degrees. So when it says pi over sine of pi over 6, that really means sine of 30 degrees. Now, it will be your expectation, or my expectation, that you know these equivalencies of these special angles pretty quickly. And I'll show you some tricks later on in a few videos to help you out with that. So then sine of pi over 6 or sine over 30, if you think about 30 degrees, it's in this triangle right here, this quadrant. So this is 30, this is 1, this is 2, sorry, this is square root of 3. So sine is opposite over hypotenuse, so it's 1/2. Pi over 2, if we convert that, now this one isn't on your paper, but you can go ahead and mark it down. 180 over pi, that gives you 90 degrees. And I think this will be good to review. 90 degrees is right here, and we have the coordinate point 0, 1. And remember, this refers to the adjacent, or the x, and this refers to the opposite, which is the y. So tangent would be opposite over adjacent, which would be undefined. 16.2 just puts into application the use of radian measurement. It has to do with the arc length and the area of the sector. And with both of these, what needs to happen is that the theta has to be in radians. So we can't use degrees. We're going to always have to make sure it's in radians when we're using these formulas. So the arc length, first of all, the arc length refers to a piece, oops, that's terrible radius. Um, the arc length refers to a portion of the circumference. So something like this would be considered the arc length. Now, if you look at the formula, it's just S stands for arc length, equals R times theta, and theta has to do with the angle right here. And again, that should be in radian measurement. Now, this should make sense, the formula, because if you think about it, circumference equals 2 pi r. Notice that the r's are the same, but what's different is the 2 pi versus the theta, because the 2 pi refers to the entire circle, whereas the theta only refers to the portion of it. Now, the next formula is the area of the sector, and you can see the formula listed right next to it. It says area equals half times theta times r squared. Very similar to what we talked about in the last one. It has to do with the area of the entire circle. Area equals pi r squared. Well, if you compare it, half theta versus pi, normally the entire circle is 2 pi. So we're doing half of that to kind of show the difference between the two formulas. And the theta refers to only a portion. And again, the area of the sector, what that refers to is, again, just like the portion of a circle, not the actually entire thing. Noting that theta has to be in radians as it was for the arc length. We have two quick examples that use both of these formulas. The first one says a rope is being wrapped around a drum with a radius of 0.8725 feet. How much rope will be wound around the drum if, that should be if rotated through an angle of 39.72 degrees. So to kind of visualize this, and this is really kind of, if you see this with chains and gears and wheels and all that sort of thing, this happens actually quite a bit. So if you have a barrel or a drum, and what happens is you have a rope that's going around a portion. So you can kind of see this rope being turned through this. We know that the drum has a radius of 0.8725. And the angle that this rope hits through on this is 39.72. Now my angle looks a little bit bigger, but you can kind of understand. So that angle refers to the amount of the rope that it's touching. So it's asking how much rope will be around the drum when it's rotated. So if you look at this right here, this is an arc. So we're going to use the arc length, which is denoted by this formula. So we're going to use theta. We want it to be in radians. So what we're going to do is I'm going to take 39.72 and I'm going to times it by pi over 180. Okay, again, we make sure those degree signs are going to cancel out. And then the radius is going to be 0.8725. I can go ahead and put this all in my calculator and we're going to round to the nearest hundredth, 0.61 feet. And finally, in the last example, I'll show you kind of the area. And if you look at this, this is area of a sector because you can kind of see that rotation. So we're trying to figure out that portion in there. If we remember what the formula is, it's area equals half times theta times r squared. Again, we want theta to be in radians. So I'm going to times this by pi over 180. And then the radius is 321. And then we got to square that. So again, what's going to happen is you can use your calculators. I'm going to put this into my calculator and we're going to get approximately 13,500. And then this should be actually square units because it is referring to an area.